Thanks so much to the organizers for organizing this meeting. I've been having a great time, and I've just been loving talking with all of you and hearing the talks and everything. I'm really excited to tell you about some work on coalescent theory and conditioning on population pedigrees, which is what we have been working on for a few years now. And this is a paper that is recently accepted to TPB, so it'll appear before too long. And these are the authors. There's Max Newman, Waitong Louis Fan, who was here and had to leave yesterday afternoon, go to another conference, and then me. And, you know, Max, this is the PhD work of Max. And, you know, he really did the heavy lifting of the math for sure. So I'm presenting on behalf of my co-authors, and I'm really excited to tell you about this. Anyway, it's about conditioning on the population pedigree, in particular when there is self-fertilization possible. And sorry, also in a Morat model, although that's a minor detail in comparison. Okay, so self-fertilization, I probably don't need to tell most of you, is common in plants. In fact, many plants do it primarily, 15% or so, 10 to 15% self most of the time. Two of our famous, beloved model species self 99% of the time, Arabidopsis and C. elegans, Thaliana and elegans. Selfing has a number of, or self-fertilization or selfing has a number of effects. It decreases variation, increases homozygosity of individuals. It, as a consequence, reduces the effective recombination rate. So this has important consequences for all sorts of things one might want to measure or think about. And it also produces this kind of odd effect of making associations between independent loci in the diploid genotypes of individuals, which is pretty fascinating. So that there are too many individuals that are double heterozygotes and double homozygotes in the population compared to what you would expect. Selfing alters the evolution of the recombination rate. It interacts with inbreeding depression very strongly. In fact, inbreeding depression and selfing sort of go hand in hand in determining each other's effects and rates. And there are many consequences of these things in any sort of evolutionary situation you would want to model. So selfing is important, and that's why we wanted to think about coalescent models in it. And this isn't the first time, but we're doing this differently now than most coalescent models in that we're conditioning on this thing called the population pedigree. The population pedigree is just the normal genealogy of individuals in the population. And the trick is we think of all of the individuals in the population or in the species, and we think about all time back into the past. So this is kind of an abstract object that you might not ever have that much information about. But we want to know, are there cases in which there are things in the pedigree, events or whatever, that affect the coalescent rates or probabilities? And the key thing is that gene genealogies across all loci in the genome are the result of transmission, through this one pedigree, which really happened in the past. This is key to me because when you do something like generate a site frequency spectrum and stare at it and then compare it to the predictions of a model, you're using the predictions of a single locus normal coalescent model that doesn't include the pedigree. And it doesn't include the pedigree in a particular way in that it averages over the pedigree. It's marginal to all the possible pedigrees that could have happened. And so what you're doing when what you're effectively doing when you look at a site frequency spectrum and compare it to predictions is imagining that each of your loci come from a different population. Right, that's sort of implicit in that comparison. And also the same thing when you multiply likelihoods across loci using a simple coalescent model, one of the standard coalescent models that average over the pedigree. The dynamics of loci within a pedigree are really pretty simple. For a single autosomal locus, we just follow things backward in time if we know the pedigree. And if there are two gene copies in me, they have to go to my two parents if I'm an outcrossed individual, which I am. A single lineage, I promise, a single lineage, 50% of the time goes to the one parent or the other. And when two lineages get to me, from my two kids, say, at the same locus, they have a 50% chance of coalescing in me, but a 50% chance of staying distinct and then going to my two parents. So all these three things are very simple to model. And I mean, I'm sure you know them already. Here's what we're doing, a very simple model. So this conference, many people have been talking about very complicated and interesting realistic models of populations. This is not one of those. This is like the simplest possible situation you can imagine constructing to answer one simple question about whether the pedigree matters or not when there's selfing. It's a constant size population model. It has this particular kind of reproduction, moron reproduction. And the difference between the normal moron model, in which normally in a moron model, one individual dies and is reproduced by one offspring every time step. And the difference here is that we allow selfing. So when that individual is produced, there's a probability, which I'm calling alpha n in here, that it's produced by selfing. 1 minus alpha n, it's an outcrossed individual. And so the pedigree would be constructed over and over by doing this in every single generation, flipping these coins for selfing and not selfing. And the pedigree itself, this picture shows the relationships of genes. But the pedigree itself would be just saying that this individual is selfed and related and descended from this one. What happens to the gene copies at the next locus you look at would be independent if it's an unlinked locus. All right, so that's the model. The subscript on alpha isn't, any statement about what is biologically reasonable. It's just there so that we can compare the relative rates of selfing as the population gets bigger and bigger. Now we should digress for a second and talk about coalescent models. I don't know if there's a light up here, but anyway, so in the simple coalescent model that people know a lot about, is the so-called Kingman coalescent, or sometimes people say standard neutral coalescent. It's a model with a constant population size, no selection, no nothing else going on, any kind of population structure. It has time rescaled so that it's proportional to, n generations. And then the coalescent time, which one might call T, pairwise coalescent time. I'm just going to write n equal to 2, would be on this time scale. And a very simple prediction, which we use a lot in this work, is about the pairwise coalescent time. And so if I write something like this, the probability density function of the coalescent time, the simple Kingman coalescent has an exponential prediction for that time. Just simple, e to the minus t, when time is rescaled in the natural way for any particular model. It would just be n in a haploid model, it would be 2n in a diploid model, the way we normally do it. So we want to know, whether the pedigree matters in this case. And so I might, instead of that, I'm going to show you a picture in a minute with the cumulative density function, so CDF. So if I think about the CDF instead, which is pretty straightforward, from that, it just looks backwards, flipped over. What we want to know is if I take one pedigree and make the CDF for that pedigree and a particular sample of size 2, and then I swap out another pedigree from the model and another one, and I keep drawing these things, what they look like on the board anyway. And in the math, we want to know whether they converge or don't converge in this limit. Oh, sorry. Super important thing about the Kingman coalescent is we're always thinking about big populations. So maybe this is pedigree 1. And then the next one, looks like that. The next one looks like that. And so on. If we find something like that, we say the pedigree doesn't matter, right? If, on the other hand, there we go. If, on the other hand, you get a picture like this one here, maybe the first pedigree looks like that, but the next one looks like this. Whoops, shouldn't it go down? And the next one, looks like this, and so on. So there's, 1, 2, 3, etc. In the limit, as the population size gets bigger and bigger, we know that there's not convergence to the average model, which is the normal Kingman coalescent, there's something else we have to think about. And maybe we can describe what these things should look like for a given pedigree. Yeah.
So just to clarify, this is CDF across loci given one pedigree?
Yeah, so you have a pedigree, you go and sample, let's say 2 different individuals and follow 1 gene copy from each of them at 1 locus. Do that once. This prediction here, this distribution, is if you were able to take a very large number of independent loci. This is, and I would argue that's how we normally use coalescent models. And for example, looking at site frequency spectra and so on. Great, yeah, and feel free to interrupt me, obviously. Okay, here's the model. Sorry, it's got a lot of parameters. There's the probability of selfing. The natural sort of timescale in the Morin model is proportional to n squared generations because only one individual is produced and dies every time step. So n squared time steps. It turns out that it's not the rate of selfing so much as the rate of outcrossing across the entire population that becomes important in these models we're talking about. And so there's this thing, n times 1 minus alpha, which is the total number of outcrossed individuals each generation on expectation. AN is going to be the pedigree, and we imagine we know which individuals are sampled on the pedigree, and I'm looking at 2 gene copies. So it might be 1 individual with 2 gene copies in it, or it might be 2 different individuals, 1 with each. Tau n would be the number of time steps back to the common ancestor. So this in unscaled time. And then we're going to be looking at the rescaled coalescent time, which is tau n divided by n squared on the time scale we're looking at. It turned out that there were 3 different things that happen in the limit in terms of the outcrossing rate. One of them is so-called partial selfing. That should be well known to anyone who knows about coalescent models with selfing. There's a model called the coalescent with partial selfing. And this is when the outcrossing rate goes to infinity. The rescaled outcrossing rate goes to infinity. So if I had a constant probability of being a selfed individual, an outcrossed individual, like 0.2 or something, and I take into infinity, then I'm in that category. On the other hand, if the rate of outcrossing is proportional to 1 over n, so really small, then we get this other thing we opted to call limited outcrossing. And in that case, in the entire ancestry of a sample, there's going to be a finite number of outcrossing events because the selfing rate is so close to 1, or going to 1 in the limit. And then finally, if you simply say that alpha is equal to 1, then this thing would be 0. Or if it goes to, if the selfing rate goes to 1 really, really fast, then this product, that's the number of outcrossed individuals in the population each generation, would go to 0 also. This is so-called, what we called negligible outcrossing. All right, so I already said there are 2 kinds of lineage samples, one where you're in different individuals, one where you're in the same individual. This is the transition matrix for 1 time step in this Warren model with those 3 states and then a coalescent state. So you can be in only, 2 lineages can only be in one of these 3 states, and we just want to know the time to go from either the diff sample or the same sample to coalescing. That's this T. Here's a theorem that's in this paper, and for any selfing probability that obeys this here, goes to infinity, where the outcrossing rate, oh, sorry, that's not true here. Sorry. This is the average model, right? This is where we're averaging over pedigrees, and this matrix effectively averages over the pedigree by calculating the probabilities of events by averaging over whether you're outcrossed or selfed. Sorry about that. And the theorem is below, and you can see for a diff sample, the bottom line, we have an exponential. It's rescaled by 2 over 2 minus s, which is the individual inbreeding coefficient. This is the known result for the partial selfing model with coalescence. And then the same sample has that in it, but it also has this factor, which is 1 minus the individual inbreeding coefficient. And so what happens is if you have a same sample, there's an F chance, or 2 over 2 minus S chance, that the 2 things coalesce very quickly in the ancestry through selfing in the ancestral lineage of that particular individual you got. and 1 minus that probability that they go to the diff configuration and then enter this Kingman coalescent style thing. This is what was known already and not for the Morin model. That's why we have this particular result. It's derived for the Morin model, but you get the same thing, not surprisingly. All right. So here's this other one. Quenched is a word that comes from like physics and other things, but it just means conditional on the population pedigree. Here's the limit theorem, and only for the diff sample. So we have 2 lineages and 2 different individuals we've sampled, and so the reason we don't have both on this slide is that there are 3 different cases, right? These are the cases I put up there. Partial selfing, the top one, which you can see is the same as on the previous slide. And then there are these other 2 things that emerged in this conditioning process. One of them is if you have this limited outcrossing model, then you end up with an ancestral graph, which means I go back along my selfing lineage until I hit an outcrossing event, and then I have this splitting kind of event. It's very like the ancestral selection graph or the ancestral recombination graph. It's the exact same process. And on that now, the pedigree gets reduced to this graph, and on that you just follow lineages and let them coalesce and so on. And that's all described in this paper. Yeah.
There's 4 minutes.
Oh, 4 minutes. Perfect. Fine. I've never seen a deadline I couldn't break. The last one, the negligible outcrossing model, is you just wait until the individuals you have sampled have a common ancestor, and that's all that can happen. And it takes an exponential amount of time, as if you're in a haploid population. And then all loci have to follow that particular thing that happened that time. Okay, so maybe I'll skip this part. One thing to note is this big equation here. Calculating these things and investigating these questions is maybe a little bit easier than it looks like. Thinking about this odd thing, the big population pedigree, we just want to calculate the expectation and the variance. You know, that's what we're doing to calculate, to look at convergence and distribution of these distributions. And in this one, the variance wouldn't go to 0 in the limit, and this here they would go to 0 in the limit. And in this particular model, we're able to describe what happens when they don't. And that's on the previous slide, that theorem. Here's some simulations that just show this kind of thing happens also in the Wright-Fisher model. These are Wright-Fisher simulations with a population of 1,000 and 3 different selfing rates. And then I'm showing also on the graph the rescaled rate of outcrossing. And so the one on the far left would be the closest one to the normal partial selfing model when that rate of outcrossing is pretty big. But you can see it's not quite all looking like an exponential. It's got some other stuff going on. So we would say that n, you know, the rate of outcrossing has to be bigger than 100 or so. It has to be pretty big to get back to the Kingman coalescent. And on the far right, we see something where it's very, very different. And here you have these jumps in the distribution because you have these events where there's a coalescent in the graph, say, and all the loci hit that and see it in their coalescent process. Okay, to compare to the previous model that averages over the pedigree, they both had this same process for the diff samples, but for this same sample, our model is a little bit different. In the old model, we just flipped a coin, F or 1 minus F for the individual inbreeding coefficient. And here we know for the individual we sampled in the pedigree, it has some number of generations of selfing in its ancestry. And that number determines the probability of coalescence for a locus from that individual. And you can describe the distribution. I think I'm totally out of time now. Yeah?
1 minute.
1 minute. Okay. Anyway, so to summarize, sometimes we can get away with using the normal coalescent models that don't condition on the pedigree. I would argue you don't want to do that just on the face of it. You should start by thinking about conditioning on the pedigree first. But anyway, you can't do that, definitely not for selfing and for a few other cases. There are 3 different regimes that we uncovered, and they're all close. They only differ when the selfing rate is very, very high, and these other 2 emerge. Otherwise, it's partial selfing with the modification that I just described on the previous slide, very similar to the previous result. And then there's this new thing that we got excited about, where there's a new kind of ancestral graph that emerged in this limited outcrossing model. And we've been also thinking about that for larger samples and whether we can derive properties like the site frequency spectrum and so on, conditional on that graph. Anyway, I should stop there. Thank you very much. here's where the paper will appear, and there was some support from NSF. Thanks.
So we'll take just one question while Diego sets up, and as usual, as usual, other questions, use the Slack.
Or talk to me afterward, even better.
That works too.
Yeah.
That's what I was saying.
Yes, so do you hope that selfing could be replaced with inbreeding, like sib mating, cousin mating, some kind of like combination of, kind of inbreeding at those levels, and then instead of that S would be some kind of other.
Yeah, no, I think that's exactly right. And I think probably almost any kind of inbreeding, there would be some pedigree effect. It might not be that big, but it's worth.
The three cases.
Yes, I think so. Yeah, or something, yes.
Tough break.
Looks like Diego's not set up. Is there another question?
I was so curious about this ancestral graph structure. So that itself is going to be dependent on the pedigree, right? Like you need to have this graph embedded in this pedigree, or and so I was curious, like in the limit, does it average out to like a graph that you can just like that comes out without the pedigree, or like how sensitive is it?
In the limit, the entire pedigree that matters for the sample reduces to a particular ancestral graph.
Okay.
Each pedigree gets its own graph, and then you can forget the pedigrees and describe the process of producing graphs only as a branching, coalescing process, just like the ancestral recombination graph or ancestral selection graph. Yeah, let's keep going.
Yeah, you can have another more since you're still not set up. Ben?
So I'm curious, do you sort of results about how this stuff depends as a function of the age of the either coalescent event or allele you're thinking about? Like, does the pedigree matter a lot more if you're thinking about rare mutations, or a lot less because now things are really independent parts of the tree?
That I don't know. That's a good question. So for this paper, we were talking about a sample of size 2, and so we haven't really gotten to rare or not rare things. I would guess that it matters for all of them, because when you put mutation in, the typical way of scaling mutation is the old style proportional to the population size, and that puts it on a longer time scale, which would be this time scale we're working on. So I think it should matter.